Okay, hello everyone. Hopefully you can hear me okay. We are moving on to chapter 3. Although we just looked at 2.1, the other things in 2.1 show more qualitative ways and more ways to analyze the behaviors, and we may reference some of those sections again, but now I want to move on to talk about linear systems and bring in a little linear algebra into this, which I think will simplify our lives on some things. Okay, so what I did was, if you want, you can print out these slides. I typed up some things on certain slides, and I might add something to those slides, and then the other slides are left blank for the most part, so you can write it in as we go along. You might want to write it in your own notebook instead of printing this out. In case you write big, you may not have enough room on the slides to write everything. And studies show that if you write it yourself, you retain it better than if you just type stuff out. Okay. All right. And so I'm gonna try to make. I don't want like going over 15 minutes because then it's hard to upload these videos. So I'm going to stop at 15 minutes if we don't get done with what I want to get through. Okay. But I don't want to go over too long either. All right. So let's get started. And a couple things. So we talked about actually in class today the undamped harmonic oscillator equation, which is given here. And as you know, K is the spring constant, M is the mass, and Y is our position function at time t. And so this was the standard form equation. Now, if we would have continued on in section 2, we would have gotten into the damped harmonic oscillator. But let's just assume we've done that. And so here's the formula for the damped. And let's see, let me use another color. And so here, notice we have that additional negative b dy over dt. And this represents the force from damping. Okay. So that's the force from damping. And we already know that this here is our restoring force. We talked about this in class. I don't know if I gave it the name too. It's also, for those physics people, it's also called Hooke's law. That's the restoring force. Okay. And this is the standard form that we write the damped oscillator equation. So you want to make sure you put those two, the undamped equation and the damped equation, put those to memory. And again, remember, M is the mass, K is the spring constant, and B is the damping coefficient. So B is the damping coefficient. And just like with the damped oscillator, how we change that to a linear system, we can also change the the undamped equation that we did in class. We can also change the damped equation to a linear system, which is given here, where dy over dt equals v, and dv over dt equals negative k over m times y minus b over m times v. Okay. If it's easier to write them underneath each other, you can. I'm writing it this way to save space on the notes, but if you're used to seeing it across, then write it across. Okay. All right, and remember again that M, K, and B are all parameters. Okay. And so when we're looking at linear systems, we often refer, and so in the case of, in terms of modeling, so the predator-prey model, we use that model in looking at any two competing species. we use the predator prey, and it varies depending upon, like you saw from the quiz, if it's a large predator, small prey, or vice versa. It's different. It can take on different forms. And so remember, so in terms of this model right here, in terms of the harmonic oscillator, it's mainly, you know, they talk about in physics and things of that nature. And for engineer majors, you may be dealing with these types of models as well. But another model we want to look at, which I'm calling the Hair Wars model. And so your book talks about 2 cafes, but I wanted to talk about 2 hair salons and looking at this and analyzing. Okay, so notice I didn't write a lot down for here, and I'm not going to write a lot down, but I'm going to say a lot about this. So you may want to jot down notes that I talk about and see if it makes sense. Hopefully it makes sense to you. Okay, so let's assume one of the best TV shows that ever came on was called A Different World. And Hillman College was the fictitious college that I always wanted to go to because I thought it was real. Nevertheless, it is not. And so, anyways, let's assume that 2 new hair salons move right next door to each other on Hillman's campus, which part of that was filmed on Spelman's campus. And let W of T be our function, be the daily profit of Whitley's salon at time T, and K of T be the daily profit of Kim's salon at time T. And hopefully everyone has seen at least one episode of A Different World and know where those names come from. If not, then you need to Netflix that. Okay. So we just start with this simple linear model. Okay, we have this simple linear model. Again, W is Whitley's daily profits at the salon, and K is Kim's daily profits at the salon. And so notice that the rate of change of their profits depends on both Whitley and Kim's daily profit and nothing else, right? There's no other factors that we're considering, so that we can call this a simple linear model. Okay. And so A, the parameter A, okay, and if we're looking at, so we're going to analyze the rate of Whitley, the rate of change of Whitley's profits per day, okay, or sometime, I guess, time T. And so because the rate of change of Kim's is similar, right? Whatever we analyze for Whitley, the same rules will apply in terms of Kim, right? So A measures Whitley's profit on the rate of change of her profit, which is dW over dt. So if A is greater than 0, all right, and W, is greater than 0, then just think about that. So if A is positive and W is positive, which means Whitley is making a profit, then, well, that tells us then we know that A times W is going to be positive, right? Okay. And so Whitley is making money. So W is greater than 0 means Whitley is making money. So Whitley wants A to be positive when W is greater than 0, right? She wants that to be positive. When she's making money, she wants that parameter to be positive, right? Because that only adds on to her money. But what if A is less than 0 and W is still greater than 0? What would that mean? So just think about what would it mean if A is negative, but Whitley W, her daily profits, is greater than 0? Well, what it could mean is that the salon is too crowded and customers leave. You can think of some other things, but that's sort of one of the things you can think about, okay, in terms of, well, if A is negative, but she's making, so W is greater than 0, but it's hurting her because A is negative. So what could that mean? So that could mean that she has a lot of clients, but maybe they didn't want to wait, okay? It's walk-ins, they didn't want to wait when they walked in, you know. Well, what about B? In that same model, what is that B representing? Or how can we analyze that B? All right. Well, So let's think about that. Well, if B is greater than 0 and K is greater than 0, so B is greater than K, remember that's Kim's profit. Kim is making money when K is greater than 0. So if B is greater than 0 and K is making greater than 0, well, this is also saying then Whitley also benefits, right? Because this is the model for the rate of change. Remember, we're still looking at dW over dt, the rate of change of Whitley's profit. Okay. And so if B is greater than 0 and K is greater than 0, then Whitley is also benefiting from Kim's benefit. So maybe Whitley, maybe there's some type of commission going on because maybe they came from Whitley's salon or she recommended it, something going on where she's benefiting from Kim's profits. Okay, I hope that makes sense. All right. And if B is less than 0, but Kim is still making money, what do you think that means? So what could that mean? Well, it could mean that, so Whitley, the rate of change, now this is affecting Whitley negatively, right? She's not profiting off of Kim's profits. So this could mean that Kim could be stealing customers from Whitley. Okay. All right. And so the similar interpretation for dk over dt. I hope that made sense. I didn't want to do what the book had. I wanted to sort of make it a little more relatable. So hopefully that makes sense in terms of analyzing that. Now what I want you to do is look in the book. So I want you to sort of go further with this and look in the book and look at figures. And I want you to put these in your notes. They might be, I think it's figures 3.1 to 3.4 on page 242 and 243. And make sure you understand, so kind of look over that, and if you want, you can think of it in terms of this if this salon problem, this model helps you understand it better, then they talk about 2 cafes, 2 coffee shops being built near each other, so you can look in terms of that. But if you want to think about in terms of the salon, think about analyze in terms of that, you can. I just want you to look to make sure you understand those graphs, because you'll have to understand them. I could ask you questions about interpreting what the graph means in terms of profits and things of that nature. Okay. All right, we are almost at 15 minutes, so I'm going to probably stop it in a minute, but let's see how far we get. Okay, so now let's talk about this in terms of linear systems and matrix notation. So now I want to go back to X and Y, just because I want to keep it simple in terms of X and Y. So let's say we have this linear system, and again, I'm not writing it down just because of space, but you can write it underneath each other if you understand it better that way. So we have these two systems, dx over dt and dy over dt. And this system is autonomous. So I don't think I mentioned this in class, but we've always talked about autonomous equations in terms of dy over dt equals f of y, right? And so, or dx over dt equals f of y. I don't know if we've talked about it that way, but autonomous means it's in terms of the dependent variables only. So even though it's 2 dependent variables, those DE models are only in terms of those 2 variables, okay? So there isn't like a T there or something like that. So that means they're autonomous. So this system is autonomous. So you can have an autonomous DE equation, and you can also have an autonomous linear system. So this is an autonomous linear system, and we have 2 dependent variables. So we call this planar. It's actually different terms, or 2-dimensional. Or we can just call it a linear systems. So don't get bogged down with the different names. But planar, if you hear planar, we're talking about 2 dependent variables. If you hear 2-dimensional, that might make it easier to remember that we're talking about 2 dependent variables. But there you have it. Okay. And so again, this might be a review, but maybe a good review for those who have had linear. If not, this is new to you, which is great. So A is a matrix. And it's a 2 by 2 matrix where this 2 represents the number of rows and this 2 represents the number of columns. For the most part, we'll just be dealing with a 2 by 2 matrix, but just in case we dive into another one, you'll know how to read it. Okay, and notice that A contains A, B, C, D, which are the coefficients of our linear system. So we call this the constant coefficient matrix. And Y over here, and this arrow on top of the Y represents, your book just bolds the letter to represent a vector, so I'm going to use arrows to represent a vector. And so this is a column vector because it's just one column. And our column vector here, or of our Y vector, which is our column vector, contains our dependent variables. Okay, so I'm going to stop this video here and then continue in the next video.